Hello. So we are back, yeah? And I know it's looking like a beginner lesson, but I think this is more for advanced people. And we will speak today about the power supply, the switching power supply, yeah? And we will discuss more about you remember the capacitors. Many people ask, yeah, why those capacitors which you remove them, why they are there, what they are doing, yeah. So let's clear and let's speak about how a power supply is working on the first place, yeah. For this, yeah, I just want to have a look on like a laptop switching power supply, yeah. Let me switch. Okay, and here we have like a classic power supply with a 51125 driver and two MOSFETs. It's a nice power supply. It's a dual power supply, 3 volts and 5 volts. Okay, let's pay attention, yeah. Not on the driver because we spoke so many times, yeah. Brush, okay. Let's pay attention about this MOSFET, yeah, this one. About this MOSFET, yeah. About this coil. About this capacitor. And about these capacitors from here. Remember, I always remove like one cap from here. And yeah, let's draw without so many details, and let's find out exactly how our switching power supply is working and how the power supply is behave, yeah. So what do we have on the schematics? What I can see there, yeah, we have two MOSFETs. I'll draw from this side, yeah, two MOSFETs. Yeah, on the picture are square, but it's not important. That's two MOSFETs. Can be channel N, on the schematics are channel N, but can be like to have 1N, 1P, yeah? That's not important, yeah? That's not important. So we have these are meeting together here. One is connected to ground, yeah? And one to plus. On the plus, what we see on the schematic, we have like 4 caps, can be 2, can be 3, can be 4, like on the picture, yeah. There are 4, but I will draw only 3, yeah, 3 capacitors. And he's saying plus B, B plus, B plus. Obviously ground. And from the middle, same like on the schematic, same like on any power supply, we have a coil, yeah, which is an inductor, because it's an inductor. It's not like a coil. that coil has a core. And the next one, what I said to pay attention, is the capacitor. We have a capacitor, plus, minus, and ground, yeah. And this is the output. What do we have more? We have the gate here, the gate, this gate, and this gate. And obviously we have the big driver, like on our case 51125, yeah. Now this is a switching power supply, okay, and you'll find this model of switching power supply on many things, not only on laptops, on TVs, on PCs, on many other things where you need current. Yes, are different power supplies, yeah. Let's say TV power supply or TV power supply. The basic one, we have the transformer. We don't have a coil, we have a transformer, yeah. We have a MOSFET, yes. We have ground, and here we have the secondary, yeah, which in most of the cases you have a rectifier diode. Always you have the capacitor. Obviously it's a basic, and yeah, this you have the output. What they have in common, these schematics, yeah, even on this one, from here you have the big capacitor, like 400 volts capacitor, yeah, and after that you have the rectifier bridge, yeah. What they have in common, let's do one more. iPhone, everyone want to know about iPhones, yeah. So the iPhone's backlight, the iPhone backlight is something like that, yeah. We have the main, but that's the catch, yeah. If you fix phones, iPhones, because the Samsung are OLED now. On the iPhones, the catch is the power supply, the backlight power supply is always under voltage, yeah. So it's from the main power rail, and you have that square coil, yeah, inductor, okay. And after that you have here a driver. It can be a MOSFET. Let's say it's a MOSFET, but you have a chip there, which is a driver, and which is switching the ground. And after that, you have a coil. You have the rectifier diode, and this is the output. Yeah. The funny thing, on this kind of schematic, like how is the iPhone, this is on the screen. So if this is not switching, the phone is off. Yeah, the phone is off, and the driver can be IC. There is IC, it's a chip. It's not a MOSFET, but the chip has inside of a MOSFET, so it's same thing. This is switching the ground. Yeah, you have always voltage. If it's not switching, yeah, you have the voltage of the battery. Yeah, so many times can happen. Lucky we have a fuse, which many people called wrong filter. It's not a filter, it's a fuse. It's a carbon fuse. And many times we see that fuse is getting burned. That's what they put the fuse. In case something goes wrong, this get burned, because you always have voltage. Here you have the battery. Yeah, this is the main power rail. If this is not switching, you have there around 4 volts from 3.6 up to 4.2 on the screen connector. Yeah. When this is switching, you have there around 25 up to 40 volts, depends of the brightness. Okay, what they have in common, it is, I don't know if it's only one cap. I think can be 2 or 3 caps here, and also we have caps here. You remember, I think we found a short, like it's on the processor area next to this cap, which the color is different from the output. Yeah, I found one shorted. I have a video when I found this shorted. Yeah, so this is an iPhone case. Yeah, iPhone. This is an iPhone backlight circuit. So if you try and find the schematics, it's like that. We have the TV and we have the laptop. What they have in common? On the common, they have, everything has a coil. This has a coil, this has a coil, this has a coil, which is a transformer on this case, because the voltage must be separately from the live. This is the live, yeah, and this is the secondary. So that's the reason why you have a transformer, you know. If we don't have to separate, and you will find a lot of schematics on actually it's not a transformer, it's just a coil. Yeah. So the coil is common. The switching device is common. Like we have the MOSFETs here. Here we have on the iPhone we have the same the MOSFET. On this one we have the MOSFET is switching. Yeah. What do we have in common more? We have the capacitor from the input. Yeah. Before the coil. Here is before the switching device. Here is before the coil. Here is before the coil. Yeah. And on the output we have the capacitor. On the output we have the capacitor. On the output we have this capacitor. Yeah. So these are some things which they are in common on all the power supplies. What they all work is very simple. So if I take this coil, yeah, if I take this end, I'll take it from here, and I will switching to plus and minus the coil. Yeah, this of the coil, I will switch to plus to minus. On the other side here, I will have voltage, I will have current. Yeah, so that's how they work. On this case, on the iPhone case, yeah, we have plus here, and this is switching the coil to the ground. Yeah, so this is a switch, it's nothing else. That's what it's doing. It's switching the coil to the ground. On this way, it's creating voltage, which the diode rectify the voltage, and we get here more voltage with what we put inside. Yeah. On this case, these are switching. Yeah. Switches. Are the MOSFET switches. Yeah. Same thing. Yeah. Here, this is the switch. It's simple, nothing complicated. Yeah. So the MOSFET is a switch. The problem is, before of this, we have TVs with transistors, like a bipolar transistor, yeah, so or bias junction. They've been replaced on these days by MOSFETs. The big difference why they've been replaced is because the current from drain to source compared with collector emitter, the current and the internal resistance. Yeah, but the main thing is the internal resistance, which is very low on the MOSFETs. So actually the MOSFET is near like a switch. So the internal resistance is like 0 point something ohms, 0.0 something ohms. Yeah, very low. So it's nearly like a switch. On the transistors, the internal resistance is more higher internal resistance, low current, yeah, and a lot of heat dissipation. Yeah, so that's what we have. That's what on these days everything is with MOSFETs, because are better compared with the transistors. Good. So we clear that. Yeah, we have switches, and they are switching even here. Yeah, they are switching the coil from the plus to the minus. So these switches are never ever the both open or close. Yeah, one is switch here. When this is getting close, this one will switch to the ground. So it's working like that. Yeah, so the coil is switched to plus, from plus to minus very quickly. How quick? 300 kilohertz. That means 300,000 hertz. Yeah, 300. The frequency, like the switch, is getting open and close around 300 kilohertz. Yeah, most of them are around there, 250, 300, something like that. All are the same. They are using this kind of frequency because going up on the frequency, everything is smaller. Like the coil is small, the capacitor used there can be small, yeah? So we found what is in common. Okay. The next thing, I said how this is working. The coil is moving from plus to minus. On this one, the same. Here is plus, and the coil is moved to the ground. Same thing, yeah? So this is on the battery side, on the iPhones. But on this side, the coil is moved to the ground. So it's shorter, like you short the plus or minus, same thing. Okay? On the TVs, the same. The coil is short to the ground. Okay? So that's the way how this works. Switching the coil to the ground. Simple. I try to keep this simple. If it's simple, a lot of will understand. If it's complicated, you know, like the school things, probably no one will understand. Okay? Good. So we have 3 schematics. Okay. The next thing. Now, the MOSFET, like how I said, is nearly perfect. So the internal resistance is very, very low. That means in the moment when something like that is switched to the ground, real speaking, yeah, the coil connected to the ground, it's a short. That's how this coil is creating high voltage, yeah. So switching the coil from this to ground, that's how you create high voltage, yeah. Okay, so we are speaking here with high currents. So here will be a high current. On this case, it is the same, high current. So just moving thing, yeah, moving the coil from plus to minus quickly. High current. They are carrying high current. Same like here. Here the current is not very high, but the voltage is very high, which is same thing. Yeah, so here we have like 300 volts, and this is switching to the ground. The transformer, a lot of energy there. Okay, good. Now let's speak about those caps from here and the output one. Why we need them? But before we speak about this, let's speak how actually it's working. Yeah, so we know the MOSFETs, they are open by voltage. And 5 volts, 10 volts, 15 volts on the gate, doesn't matter. That voltage will open the MOSFET. Yeah. So the signal on the gate, 0 volts, here is 0 volts, yeah, is going straight up. Straight up. This is not, yeah, straight up. Yeah. It's staying open how long he need, and he get close. Straight down. What does it mean? Does mean the MOSFET get open on the top. Let's say we have plus 10 volts on the gate, yeah, plus 10 volts or plus 15, I don't know, depends how much voltage you need to open the MOSFET. Each MOSFET is different, can be opened by 5, by 10, by 20, yeah. So if we here we have 0 on the gate and no delay, plus 10 volts, the MOSFET will get open. Yeah. How long it will stay open, that's how you adjust the output voltage. And that's how you adjust the current on the circuit. So this can be like that, or this can be like a full sinusoid, yeah? Something like that. Yeah. But obviously, it don't need us to be like that. Yeah. That's how you adjust the circuit, the current, the output voltage, everything. Just moving this, making this bigger or smaller. How long the MOSFET will be open. Here, yeah, let's be sure we have on the same time. So what is doing this on the same time? So on the same time, if this is close, so probably this is here is open. Yeah. when these get close, this MOSFET, yeah, this is getting open. So here we have 0 on the same period of time, yeah, 0 volts. When these get close, these get open. Here is 10 volts, yeah, 10 volts plus 10 volts. So that's how they work. When this is close, it's no passing current. This is open. This is open. The current is coming here. Get close. The next one get open. Goes up and get open. And it will move the coil to the ground. That's how they work. Obviously this is going on and on and on. So this is open. Okay, this get close. This get open again. And it's keeping like that, yeah? That's how a signal on a power supply looks like, yeah? That's how it looks, yeah? Okay, simple? It's simple, it's nothing complicated. The next, let's speak about that caps. But before speaking about that caps, I want to speak about something else. Let me get another paper. Let's speak about amplitude modulation. If you ever heard about that, yeah? This is an old term, was used on radio on the beginnings. Even now, if you go on the AM, you'll still find radio transmitting on amplitude modulation, yeah. It's not used anymore. So they use on these days frequency modulation. Well, let's learn, and after that you'll understand why this modulation is important to understand how the power supply is working. Okay? Okay. I don't want to jump from something. I don't want to speak about this. I want to speak about this cap. But not yet, yeah? Not yet. We'll speak after. Amplitude modulation. How you can do amplitude how this was done before. Yeah? So the amplitude modulation, it does mean you have a fixed frequency, fixed one, yeah? Fixed. Fixed frequency, and on the schematic is looking like that. So this is going inside. You have the frequency. Let's say I don't know, any frequency. The long waves starting from like 150 kilohertz up to like 300 kilohertz. The medium frequency, I think, is starting from 500 or 600. On the medium frequency, you'll find probably radio transmitting on amplitude modulation, yeah? Okay. So we have like a, let's say a transistor, yeah? So we are coming on the base with this signal, constant signal. This is ground, or MOSFET, or whatever you want to be, yeah? And here, we have another coil, yeah? So here we have a coil. And from here is going to plus. Doesn't matter what. You can connect even a capacitor here. But that's how the amplitude modulation is working, yeah? So here we have a coil. Here you can say from here, yeah, from here, or we can see from the coil, but it's not important, yeah? Actually, this is not a coil, it's a transformer. So here we have antenna. It's transmitting waves. This one, it's a classic amplifier. We have a transistor, we have a coil, we have the antenna. It's amplifying the signal. It's nothing weird, nothing complicated. Yeah, that's how a final RF amplifier is looking. Transistor, coil, and we have the signal, which we can use the signal. But this is a transformer. So that means we have a core and we have a second coil. Okay, and here we have core. So on this one, if I come from the output of audio amplifier, yeah, like a normal audio amplifier, nothing special, yeah. If I come with the output here, and obviously with the ground here, yeah, that's the way how you modulate a signal, amplitude modulation. So this is a classic amplifier. We can, no, you know what? We can even draw the capacitor of the amplifiers. If you play with amplifiers, you know it's an output capacitor. So if you try to replicate this schematic, it will work because that's how the amplitude modulation is made. So the audio amplifier, yeah, is modulating the power of this transistor, yeah. So that's how it's doing. It's modulating by this transformer. Is modulating the power. That's what is modulating, the power. Okay. Modulating the power. Obviously, this switching based on this frequency. What we will have on the output? So let's say here we have something like that. We have the audio signal, which is looking like that. Let's say this is it's audio signal. Okay, this is audio, and this is the base frequency, which is a fixed frequency. Yeah. Here on the antenna, we will have something like that. We will have this frequency. Yeah. Will be something like that. Yeah. Sorry for my drawing skill, but you got the point, yeah? So you will have something like that. So actually the waveform will be like that. So you understand? So this will be modulated by the audio signal. So will not be like that equal. It will depend the amplitude, yeah, amplitude, that means the power, yeah? The level, yeah, will be defined by the audio signal. So on the output we will have this frequency, which is like that, modulated by audio, how you are speaking on the input of the amplifier, let's say, yeah. So that's amplitude modulation. The other modulation is the frequency modulation, which is very simple. You can't do it like that. So you will modulate the oscillator. What is the name? 1 second. Oscillate. Now how do you anyway, a frequency oscillators. Okay, oscillators. Anyway, you modulate the generator, yeah. So the frequency generator, yeah, frequency generator, let's say, which is creating the frequency. On these days, all the FM area, it's frequency modulated. That's mean, yeah, that's mean FM, yeah. So the audio signal is coming here, audio, on the oscilloscope. Anyway, the frequency generator, yeah. And on the output, you'll have, based on the voice, you'll have something like that, or the frequency get changed, yeah, and obviously can be like that. No, sorry, the level is the same. The level is the same, but the frequency is different. So actually more space here, lower frequency. Okay, that's how, but that's not important. I want to speak about amplitude modulation, yeah? Okay. What do I speak about that? To understand what happened here. So actually, each of these power supply, it will modulate, amplitude modulate, yeah, the power supply. That's the point where I want to be, yeah. So each of these one is modulating the power. Okay? Just because it's a load, just because it's a switching load, it will create a power modulation. Yeah? So just think, yeah? This, or let's say, or this, everything, yeah? So here we have a switching thing, yeah? And my plus is going on the board, yeah? It's going through the motherboard, all the motherboard long, and from the motherboard it's going to the charging port, the plus line, yeah? And from the charging port it's going to the charger, which is like probably over 1 meter long. So we have a long track, yeah? So this plus is very long. And apart the fact it's long, it's a wire, you know, and any wire which is passed by electric current is creating like it's behaving like an antenna, yeah. So any wire is an antenna, okay. So based on this, let's say here we have 0 volts. 0 volts. Here we have 19. In this case, it's a laptop power supply. 0 volts, yeah. And here we have 19 volts. Yeah, so that's how it looks if you try to see with the oscilloscope. A power supply, it's a line, yeah. If I take out these caps, my line will be like that, will be according with this. So I will have something like that. Because these MOSFETs, if you see this MOSFET, everything from here is like a switch to ground, yeah? It's a load. Everything is a load from here, and it's switching to ground, yeah? And that's how the power, my power rail, will looks like this. Okay? If you know how the capacitor are working, on the DC, yeah? DC is not passing the capacitor. Actually, a capacitor gets charged or discharged, but it's not passing to the ground. So a capacitor, it's like a resistor when it's about AC, and this is AC. Okay. What can I say more? That's the main reason why these capacitors are here. So it's passing this, yeah, any frequency, which is this signal from here, from the output, is reflected to the power supply, to the power rail, yeah. These caps are meant to put everything on the ground. So any kind of, you know, any kind of frequency which is, it's normal to be here, it's normal. That's the amplitude modulation, yeah, like how I explain you. Any signal, like anything what is going out from this power supply, is going to the ground through these capacitors. Yeah. If you don't have these capacitors, yeah, let's say we don't have this capacitor, what will happen then? Well, let's say we'll have a long antenna which is going up to the power supply of the laptop, yeah, through the wires and everything. So you'll have a long antenna which will radiate this frequency, 300 kilohertz. Okay? So you know, using like 3 capacitors, this is putting the ground something, this, the next one is the same, the next one is the same, yeah. But that's not the only thing why those capacitors are there, and we'll speak after about the second things why the capacitor are there. Okay, so that's what the capacitor is doing. Same here, switching this to ground, he will create here same thing, this. Okay, now you'll ask, okay, but why this is important? You know, we have a filter, we have like a filter on the charger, or we can you know, we have capacitors on the output, on the input of the charging port, so we can cut down there all these problems. Yes, but it's the second problem. The second problem, you don't have only one power supply like that on the laptop. Yeah, like 5 or 6 or 7. You have a lot of power supplies. Now, if you come with a voltage, with a modulated voltage, you will modulate the power supply itself. Yeah? So, that's the second problem. This kind of signal, which is going on the B, yeah, on the main power rail, can modulate another power supply. So let's say here on the output we have something like that. Yeah. If I modulate this power supply with this signal from the plus, yeah, let's say we have another power supply next to it, yeah, but even that power supply has caps. So the people think, you know, even that power supply has another caps from same reason. One is not coming nothing inside, one is not going nothing outside. Yeah. So we will have the signal like that. So the signal will be the same, the switching, but you can see some small spikes. Yeah, and those spikes can be anywhere. Something like that. You can see something like that, some spikes, which they are coming from the power. And obviously these spikes can, you have the feedback. So somewhere you have a feedback from here to the chip, and the chip can get wrong about how much voltage it's on the output. He can get like the top spike of this, say, look, that's the voltage, so we have to lower the voltage, but actually the main voltage is here. But it's nothing like that. It's you understand, the people, they are building this power supply, they think, and each power supply they have these caps. Yeah, on each one you'll find caps on the power supply. From this reason, nothing go out, nothing come in. Simple? Yeah, nothing complicated. Okay. One more thing, yeah. The second reason why the caps are here. How can I explain you that? I have a capacitor and LED here, which I meant to show you what happened with the output voltage. So the output voltage is like that, yeah, square. It's not square, sorry. Yeah, it's something like that. And the capacitor, obviously the capacitor is smoothing the voltage. So after the capacitor you have a line, because that's DC. The way how they work, a switching power supply, I will show you, yeah? A small experiment. Yeah, let's show the experiment. And I will tell you after that why this experiment is very important with this. Yeah? So what do we have? We have a power supply, my power supply, minus, plus. And we have minus is the same. The first thing, it will be like that. On the plus, we have a multimeter, which is on ammeter right now, so we can see the current. Yeah, ammeter. I want to see the current. Yeah, that's what I'm looking for. And here we have a switch, which I'm doing switch. I'm a switch. I will switch myself. Yeah, and we have a LED. We have a resistor and a LED. So basically, when I connect this to this thing here, yeah, when this will be a circuit, the LED will be on, and I can see how much power it's taking. Yeah, this is a nice multimeter, cheap one, but you will understand this multimeter, which is a proper cheap one. I think it was like £3-4, is doing something which like no digital multimeter is doing. Yeah, actually with a multimeter with this you can see pulses, yeah, or spikes. With the digital one you can't see that. You will see only numbers changing. Okay, so that's why it's important always to have something like that around you, in case you have a power supply which, I don't know, is doing weird things, and if you can't see with the digital multimeter, you can see with something like that. Because actually with this you can see exactly the current, yeah, the voltage, the current, depends what you're looking for. So when I'm connecting the LED, yeah, just ignore the capacitor for the moment. You can't see the capacitor anyway, that's good. Yeah, so the LEDs is on, and yeah, I think it's too much current. This is 0.5. The LED is on. Yeah, so now in this moment I am a switching power supply, like 1 Hertz power supply or 2 Hertz power supply. Yeah, now I'm switching. That's how the MOSFET works on slow motion, like exactly what I'm doing now. And that's the current from the power supply. Yeah, okay, the next thing, let's add the capacitor. Yeah, let's add to this circuit, which I'm switching here. I'm switching me. This is Sorin. Let's add a capacitor, big one, because we have low frequency switching. Yeah, big one. Let's add a capacitor here, 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 plus, minus. Okay, and let's try and switch now. Yeah, so we can see exactly what happened with the multimeter when I'm switching. I just want to check, to look on the needle. So you can see what happened. Obviously this is normal, but the switching power supply is working on the same way. It's switching exactly like me. Yeah? Probably more stable, yeah, and a lot more fast. Now let's connect. Yeah, I connect the capacitor, so now the capacitor is connected, and I will do same thing. I will do exactly same thing. Yeah. And let's try and switch again. So you understand how this works? The problem is the multimeter has a very high resistance and the capacitor gets charged slowly. But you got the point, yeah? So everything is smoother. There's nothing jumping like crazy, yeah? If you... Even this multimeter, he cannot see the spikes. But actually the spikes are very high. But if I'm just touching, you see a move here. But the spike is a lot more higher, yeah? So connecting to a capacitor, the capacitor is getting charged. This is the output capacitor, yeah? The output capacitor. Output capacitor here. This is the output capacitor from this one. Yeah? From this one. Or from this one. The output capacitor. Yeah? So that's the way how a capacitor is smoothing the current. One more time, multimeter. So it's nothing jumping like crazy. Again. It's nothing like that. So actually everything is a lot more smoother with the capacitor. You can see. Okay. That's the way how the output is creating for something like that. Something like that, like a line. Yeah. Now here, yeah, even this capacitor, it's working on the same way. Now, what do I mean with this? Actually, if you understand here what happened, this is a big thing. Yeah, just to understand what happened. So actually, my LED yeah, my LED yeah, taking a lot of power from this capacitor, yeah, on this way, and my power supply charging constantly the capacitor. Yeah, that's what it's the smoothing thing. Yeah, that's how they work. So I'm supplying constant energy here. Yeah, but this, even if switching, yeah, it's not taking power, let's say, straight from the power supply. It's taking apart from the capacitor or the spikes. I would say the real thing is taking the spikes from the capacitor. Exactly like on this case. Yeah. So actually each spike, let's say when this, because it's a power, this is a spike. You see this one. This is a very high current. Yeah. Very high current. First it will take, on each spike it will take the energy from the capacitors. Yeah. Okay, that's the second reason why those capacitors are here. Just being capacitor here and taking spikes like how I did, I switch here, yeah, everything here is smoother, yeah, so I will not have big spikes like this by amplitude modulation on the plus line, on the power rail, yeah, because when it's a spike it's a direct access on full power from the power rail, it will take from here. But those capacitors are small because the frequency is high, and actually the spike it's you understand, it's a spike like we have 300,000 per second. Just a small spike which will be taken by these capacitors. So these are supplying power to the capacitors, and the power supply is taking the spikes, so it's taking the power from the capacitor. Yeah. What is happening on the real on the real life, not on the paper, it's happened like this, but from let's say a full switching, from the caps they are taking like only the spikes, only the top, yeah. So on the top, which is like high current is not coming from the plus line. High current is coming from the capacitors, yeah. So the capacitors are able to supply high current. Compare with the power line. Okay, when it's about a spike, a short spike is mean one spike from 300,000 spikes per second. So 300 kilohertz is 300,000 hertz. Yeah. Okay, so we are speaking about one from this number. So you understand how it works. So actually you think the power supply is taking power from the power rail, but no, each spike is taken out from the capacitor. Okay. On the other words, these MOSFETs are modulating the power rail, yeah, are modulating the power rail, but the capacitor are putting down any frequency which is coming out from here. Okay, so they are doing two things, those capacitors. Which many times I remove one, or on the iPhones, same thing is doing same thing, no difference. Okay, that's how a power supply is working. Yeah, obviously that's why they are there, because many ask why they are there, why you remove them, why you don't replace them. Let's say you have 3 caps. If you remove one, everything will be fine, will be no difference. Yeah, are important, but everything can survive even without. Even if I took out these all 3 caps, the power supply will still work, because the chip, it will compensate any drop of the voltage or drop of current. Yeah, the power supply, it will compensate. But just to be everything is smooth here and I have no interference, yeah, outside, yeah, those capacitors are very good to be here. Okay, that's why that capacitor are there. So hopefully I clear this and you understand how the switching power supply are working, in case you ask how the switching supply are working. Same thing on the TV ones, same thing on the iPhone. Where is the iPhone one? Same thing, yeah, on the same way. Obviously you don't want those spikes to come back and go and modulate the power supply, the processor power supply, the power management chip. Okay, good. So I'll stop now. And I'll say thank you for watching. Please leave me a comment if it's something wrong, I'm a human, I can be wrong. I try to speak on a simple language, but yeah, the things can go very complicated if you try, and you can actually calculate everything with a lot of mathematics, which I'm not very good with the math. Yeah, even the coil, even the switching, we can go through the Lenz's law with to calculate everything, but that's not me, you know. I'm finished and I'm done with this from long time ago, from the school. Yeah. Thank you for watching. Like and subscribe if you like the video, and see you probably tomorrow from work. Yeah. Bye.